accordingly, right? So it is our duty to let you know that how we are going to assess you, and you have to prepare accordingly. uh, I would definitely try to impress more upon the basics. So in MCQs, I would prefer to ask more of basics. In short answer type, I would prefer to ask, I would break up a big subjective type question into smaller objective types, right? And we've had a very good experience with Google Forms. I think we can go with that only, because LMS I heard is crashing. So once everybody logs on at the same moment, it crashes down. So we would prefer to take your quiz on Google Forms. I'll look for another option. I just got to know there is Kahoot is also one option. So let's see what we can work on, right? So dates, you will have, this has to be done before, I guess, 10th of November, the mail that has reached us. And we will try not to have a clash with other subjects. Let's see if they can provide us with a, if the institute only gives us a timetable kind of a thing, a date sheet kind of a thing, wherein they have planned out all the quizzes. Let's see. So no dates right now. We will discuss with the HOD and then communicate the dates. Any doubts that you want to ask regarding the MSTs, you're most welcome. No doubts?
Ma'am, what will be the time duration of each quiz?
Most probably 10 to 12 minutes, not more than that. See, if we are giving a numerical which I take 5 minutes to solve, I will give you 6 minutes for it, right?
Okay.
So that will depend upon the kind of question paper that we said.
Okay.
Anything else? Nothing? Okay, should I start with the new topic? I just have 58 participants in my class. Why the strength of students is falling so drastically? Even though I'm uploading the lectures, I upload them after a long duration. So somebody who's missing the current lecture will not be able to cope up with the next ones. It is your own loss, but you must come for the class. It is for your own good. You're paying so much. Anyways, so let us just have a quick revision of what we've done till now, and then we'll move on to the last topic of chapter number 3. After this, we'll start with memory hierarchy. Okay, so in our previous lectures, we have discussed a few things. First of all, a DLX and pipeline machine, right? And that it has 5 main stages. So we have the fetch, decode, execute, memory, and write back. Then, in order to improve the speed, we started pipelining. What is pipelining, anyone? Pipelining
Ma'am, pipelining.
mhm,
Yes, ma'am.
of
Pipelining is the introducing parallelism among the instructions.
Very good. So parallel execution of instructions on the same hardware. So if the current instruction is moving ahead, the next instruction is just behind it in terms of hardware as well, right? And then we encountered a lot of problems for this pipelining to be feasible. So we introduced pipeline registers, right? These were 4 in number, connecting 5 stages. So we required 4 pipeline registers. And then definitely these are nothing but latches or buffers only. And they introduce some delay into the pipeline. So if we just talk about individual instruction execution, that might take a little more time now to execute. Just a minute, let me see if I'm recording the lecture or not. Then I need to upload this also. Yeah, it's getting recorded. Yeah, so the pipeline registers, they introduce some delay into the pipeline, and per instruction, if we calculate the individual instruction time, no doubt increases, but on a whole, when we calculate the average instruction execution time, say for millions of instructions, this improves in speed by many folds. Typically a best speed up would be a speed up of 5, but there are certain limitations which do not let us achieve a speed up of 5. So we get somewhere around 5. And the average CPI that turns out for a ideal pipeline machine. So I should write average ideal CPI. कितना आता है?
One.
Yeah, very good. So we get an ideal average CPI of 1 in a pipeline machine. Then we discussed that even though after introducing pipeline registers, the parallelism among instructions led to certain problems, and these were called hazards, right? And in the hazards, we had three main categories. We had the structural, we have the data, and we have the control hazards. Now, Sarthak will tell me. Sarthak, what is a structural hazard? Sarthak, unmute yourself, bache. What is a structural hazard?
Yes, ma'am.
What?
Ma'am, basically, when two instructions that are in the pipeline already need the same resource,
Right.
like yes, ma'am.
So absolutely right. If there is a hardware clash, if there is a resource clash while parallel execution of instructions, and that resource, if it is limited, so maybe same register written or read to, maybe the same memory location written or read. So at the same moment, either one instruction can use it or the other one can use it. This leads to a structural hazard. Savi Serene will tell me how do we remove structural hazards.
Yes, we removed the structural hazards by adding the stalls or the bubble in the pipeline.
Very good. So by default, the processor compiler, which has a very strong control logic, a very efficient control logic, it realizes that this structural hazard can be resolved by letting the first instruction use the hardware, the required resource, and delaying the next instruction by one clock cycle. So which is actually introduction of a stall into the pipeline. All right. The next type of hazard that we encountered was a data hazard. So Janvi will tell me what is a data hazard. Janvi, unmute yourself, bache. What is a data hazard?
Yes, ma'am.
What is a data hazard?
Ma'am, data hazard is caused when same registers, basically registers are used, same instruction fetch and instruction decode memory,
Is that
IAM
data
and
hazard?
ID.
Is that data hazard? No. Nehal, Nehal Arora, unmute yourself. Hanji.
Yes, ma'am. Ma'am, data hazards occur when suppose an instruction, maybe it's a load instruction, and it is execute in the fourth stage. It gets the value from the memory, and suppose the next instruction requires that value, but it has not currently fetched the value because of pipelining.
Right. Okay, very good. So we can have data hazard in the pipeline when the current instruction has not yet produced the result and the next instruction reads a wrong value. So that was a raw hazard, if you all can recall. So that was a raw hazard, the most common data hazard that happens. But we do have a write after write hazard also, and a write after read hazard also possible. So the names, again, I'll just quickly brush up. The names actually identify the correct sequence. So if I have an I instruction followed by J, I should write first and then J should read. It should be read after write, right? And if the other way it goes out of the order, the present instruction has not produced the result and the next one it uses it, it causes a raw hazard, which is the most common one. Now, Yug Chaudhary will tell me how do we remove the data hazards? What is the best way to remove data hazards?
Ma'am, stalls and bubbles.
Is stall a viable option for a data hazard? We have so many data hazards in the pipeline happening.
Ma'am,
Stall is
don't
not a
know.
viable option. Anything else? Who will tell me? Jashika. Jashika, how do we remove data hazards? Most of the times, we don't want to introduce a stall into the pipeline. So how do we try to
Ma'am,
remove it?
data forwarding.
Bilkul. So we have data forwarding from the stage that intermediately produces the result to the stage that immediately requires the result. So whatever was read in the previous cycle is bypassed, and this forwarded data is taken as an input to the ALU. So we had three forwarding paths available. Anyone who can tell me from where to where? Rhythm, can you tell me? Rhythm, can you tell me from where to where do we have the data forwarding paths?
Ma'am, I don't know.
Okay, we were to have exams in this week. Vartika Singh, would you like to speak up? Vartika, what are the data forwarding paths that are available? No? Anyone who would like to voluntarily tell me?
Ma'am, can you please just repeat the question?
The question is that if I talk about forwarding path, right?
Yes,
We
ma'am.
just have three forwarding paths available in the hardware. What are those?
Ma'am, from the ALU to the memory,
Mm,
ALU of the first instruction to the memory of the second, and from the instruction register to the ALU of the next, and the third one being from the memory part of the first to, ma'am, third one I'm not sure of.
okay. So here we have the 5 stages, right? And here we have the pipeline registers also. So we have the pipeline register here, 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 and here, right? In the hardware, we just have three feedback paths or data forwarding paths which are available. This is from here. If you all remember, I had shown you this diagram in the class. So this arrow is going opposite. But anyways, if you can just understand, from the output of the memory oblique write back pipeline register to the input of ALU. Then one was from here again to here. So the output of the execute oblique memory register to the input of execute stage, which is the ALU input. And the third one again is from here to here. So one is for data forwarding and one is for LMD data forwarding. So load memory data. I hope this is getting clear. This brush up is required. I have to cover a new topic today. I hope this is fine, everyone.
Yes, ma'am.
All right. So these data forwarding paths, when we see in time, you see them as forwarded paths actually. So right now you are seeing it as a loop which is coming back to the input stage of the ALU. But with respect to time, they are actually forwarding data from one stage to the other. And that is why these are called forwarding paths, right? So we have this forwarding, the control logic of the DLX processor, which is responsible for activating the forwarding paths as and when required, and it avoids the introduction of a stall into the pipeline. But there are certain instructions like load, which is accompanied by, say maybe I have a load say into R1 from say 0 R2, right? And next it says add say R3, not R3, I can take R5, R5, R1, R2. In any case, for such an instruction, the output for the first one intermediately is available after the memory stage, and this requires the add instruction requires the input at the execute stage. So here, introduction of a stall is mandatory. So we cannot do without the introduction of a stall. Even the forwarding paths cannot do anything because something which is available at the end of clock cycle 4 and required at the input of start of clock cycle 4 cannot be done until you have to wait. So until you introduce a stall. So this stall is mandatory for such instructions. Now there was a rule that whenever a stall comes into the pipeline, the forwarding paths are deactivated. You know, we discussed this also. So by automatically this happens. So the moment there is a stall in the pipeline, all the forwarding paths, they are deactivated. They cannot now forward the data. Then there is a hardware which is responsible for introducing a stall also, and allowing the forwarding paths to get activated. Aman Mittal will tell me what is that hardware called. What is that hardware called, bache? Aman Mittal, speak up. Okay, Aryan, would you like to speak up? Aryan, see, if you don't respond, I feel that you've left the class. You've just logged in and you've gone somewhere else. At least speak up and tell me, ma'am, मुझे नहीं आता है. You know, whatever is there, even if you speak wrong, I can correct you out. You can try at least. Yes, Aryan, will you speak?
Ma'am, I don't know.
Okay. Siddhant. Siddhant Khanna, will you speak up? What is that hardware called that introduces a stall also into the pipeline and maintains the correct sequence of forwarding? It's a very important hardware. You might expect a question in the quiz also. Anyone from the entire class right now?
Pipeline
interlock.
Yes, it is called as a pipeline interlock. So this is the control logic, the hardware with the respective control logic that enables the DLX processor to maintain the correct sequence of stalls and the forwarding paths in the pipeline. All right. Now, coming to the third type of hazards, which are control hazards. When do control hazards arise into a pipeline? Anyone?
branch instructions.
Right. So suppose we have, say, add R1, R2, R3, and then we say, branch if it is not equal to 0, if you want to check R1 to say, say target 1, and then you have an instruction, say subtract R6, R7, R8, and then you have another instruction which says, say, load word into R5 from, say, 0, R3, and then you have an instruction which says target 1. So this is target 1 and it says, say, hold, for example, right? So for this code, if it is pipelined using this DLX processor, after branch instruction is pipelined into the hardware of the with the hardware of the processor, next 3 clock cycles, I'll just write down the stages so that it becomes clear to you. Just a minute. Just try and, is it visible? ये सब नजर आ रहा है? ये overlap तो नहीं कर रहा है?
The bottom part is overlapping, ma'am.
हाँ, मैं थोड़ा सा ना इसको अभी अगर डिलीट कर दूंगी तो क्लियर हो जाएगा. या so I think it's fine now. Right. So if I just write down the stages, it is fetch, then decode, then execute, then memory, and then write back. Right. Now, suppose this the current clock cycles show the fetch of the branch not equal to 0 instruction. So after the branch not equal to 0 is fetched and it goes to the decode stage, by that time next 3 instructions, so one fetch here, then decode, then one fetch here, and one fetch here happens into the pipeline, right? So once the branch instruction is fetched, it goes to the decode stage. The next instruction is by default, which is subtract instruction, is fetched into the pipeline. It goes from decode to execute. The next instruction, which is load word, is fetched into the pipeline, and after it goes from execute to memory, the next instruction, which is again the fetch of halt, happens in the pipeline. But say it was a taken branch, and at the memory stage, the processor realizes that it is a taken branch. And if it is a taken branch, these three instructions should not have been fetched into the pipeline. It should have directly fetched the halt instruction. And this causes a change in the actual outcome of the main program. हमने क्या fast किया अपना processor? हमने तो output ही disturb कर लिया पूरा. My program will not give me the results which I wanted it to do. So this leads to a main problem. See, branch hazards or control hazards are the worst. They lead to a lot of loss to the pipeline, and these hazards are called control hazards, right? ये हमने सारा detail में पढ़ा था. But then we discussed that we have two ways of removal of these hazards. So anyone who can tell me what were the two ways? अब ये एग्जाम के लिए नहीं आ रहा है, बट आगे वाला तो करना है ना. So we had static and we had dynamic, right? With static and dynamic, both software and hardware based techniques are involved rather. And with dynamic also we have software as well as hardware based techniques, right? So for removal, we would like to, the way we are controlling data hazards and the way we are controlling structural hazards, we would also like to control these branch hazards or control hazards. We don't want them to cause a loss to the pipeline. We would want to get the maximum speed up from this hardware, right? So we discussed some compiler based techniques, which were software based static, and what was the hardware based static technique? Anyone?
Addition of extra ALU
Yeah.
at decode stage.
Very good. So the use of two ALUs at the decode stage. So I'll just cut this at the ID stage, right? So compiler based techniques were flush the pipeline, flush or freeze the pipeline. Then we had predict every branch taken, predict every branch not taken. Remember?
Yes, ma'am.
Right. And whatever be the scenario, the processor would behave. See, the compiler is pre-programmed according to an algorithm, which says that you have to predict every branch taken or maybe not taken. So in any case, it is going to predict the target, get the target value as the next instruction in the pipeline. But anytime it fails with its prediction, a new instruction after introduction of a stall, the fall through one is fetched into the pipeline, right? Okay. And if I talk about the dynamic techniques, so I'll write somewhere else. So anyone, the dynamic ones?
Ma'am, the first one is branch delay slot.
Yeah. So we have, again, we have here software as well as hardware based techniques. And if we talk about software, we had the branch delay slot, wherein first of all, see, the first thing that we were doing was introduction of just a minute, I am getting a lot of noise from outside. I'll move into the other room. All right. So we have this branch delay slot, when and after the branch instruction, see, the first thing that we assume here was introduction of two ALUs at the ID stage. Secondly, in the branch delay slot, we introduce an independent instruction. So if you all can recall, even if we have an extra, ये याद आ रहा है सबको?
Yes, ma'am.
So even if we have an extra ALU at this stage, still one delay slot, one stall was required, because the processor has to wait and then identify whether the, what is the target address for the next instruction to be fetched into the pipeline. So why wait for this clock cycle also? The processor can introduce an independent instruction here. So whatever fetch that takes place is for the independent instruction, and this is the best technique if used properly, if we have independent instructions in the pipeline, right? Then we discussed some more dynamic techniques which were based upon hardware. Anyone, what were those?
Ma'am, bit prediction.
Right. So, excuse me, we had a 1-bit predictor and we had a 2-bit predictor. And what was a predictor? Anyone? Yashrajit Malhotra. What is a predictor? बोलो भाई, मुझे लगता है आप लॉगिन करके भाग जाते हो. फिर मैं कैमरास ऑन करवाने शुरू कर दूंगी. ओके, Saksham, I don't think he can speak. His mic is not showing up. Sukhamvit Kaur, will you speak up?
Yes, ma'am.
What is a predictor, बच्चे?
Ma'am, I have no idea.
Okay. Anyone who can tell me what is a predictor?
Ma'am, a predictor is a thing. मतलब it's a buffer wherein the branch is taken or not taken based upon the state of the branch history table.
Very good. So here we work upon probability theory. There is a buffer which stores the state of previous branches in the pipeline. If the previous branches were taken, the state of the buffer is maintained accordingly. And if the previous branches were not taken, the state of the buffer is maintained accordingly. Right? We'll discuss what the states are. Now, if the previous branch, maybe out of 9 branches are taken, there's a high probability that next branch will also be taken. Right? So we work on probability theory here. And this BHT is just a 1-bit or a 2-bit buffer capable of storing 1 or 2 bits of information. It stores the state of the previous branches, the current state of previous branches in the pipeline, right? So if the previous branches were mostly taken, there is a high probability that next one would be taken. And if previous branches were not taken, there is a high probability that the next one will also be not taken. Well, our prediction does turn out wrong sometimes, but then these predictors, this one had an efficiency of, I guess, 80 to 98%. And this one had an efficiency of, I guess, it was 1. So 90 to 99%. See, with such high accuracies, there is just a mere chance that we will mispredict. And now, what happens? Whenever the current branch instruction is fetched, along with it, the state of BHT is also fetched. If the previous state was taken, the next state is predicted taken. And the next instruction which is fetched into the pipeline is fetched from the target, right? And if the previous branch is not taken, the next is also predicted not taken. And the next instruction that is fetched into the pipeline is from the fall through. We discussed the state diagrams as well, how these states are changing. So I'll not take up again this in a lot of detail. So बहुत detail में कर लिया. Just for a quick review, we have discussed all what we covered in this chapter. There's just one thing which is left, which was pipeline scheduling. Anyone who can tell me what is pipeline scheduling? What is pipeline scheduling? Oops. Anyone?
Ma'am, rearranging the instructions. For
Right.
example, if there is a branch instruction and we predict that the branch is taken,
Yeah.
then we take the next instruction to be the target instruction. Otherwise, we take the next instruction from the fall through.
Okay. Kind of you are somewhere nearby. When we talk about pipeline scheduling, actually, we talk about rearranging the code. Maybe we do not get a independent instruction, or maybe we do not get a target, or maybe we do not get a fall through instruction. It is just that wherever a stall is required, the compiler, it inserts instructions between those two places where a stall is required. Now what happens? This instruction had to be executed either earlier or after the current instruction. and its execution at this place might not make any difference to the pipeline. So I'll just write an example for you, and I'll move on to the current topic, which is related to pipeline scheduling only, right? So maybe the current instruction says load R1 from say 0 R2, and then it says say add R1 comma, not R1, say R3 comma R1 comma R2, and then it says store R3 to yeah, so maybe 4 R2, and then it again has to load the next value. So it is from into R1, 2, 3 I've used, R4 from say 8 R2, and then again it says add R5. So R5, R4, R4 and R6, for example. Excuse me. And it says store word from R5 to say 8 and then say 12 R2. Anyone who can tell me from the entire class right now, where all do we require a stall in the pipeline currently?
Ma'am, after the first instruction
Right.
itself.
Absolutely right. So we need one stall here. This will produce the result. I'll just write, I can write it here. So fetch, decode, execute, memory, and write back. All right. Now, for the first instruction, the result intermediately is available after the memory stage. And if we have the next instruction, which is pipeline with it, it will require the input here. So decode and execute. So if we just observe, the moment I leave this writing pad, I'll freeze on this. Okay, never mind. So if you can just see my cursor, I have the intermediate results available after the memory stage, while the input is required at the beginning of the execute cycle, same clock cycle. There's no option. This instruction has to wait for one clock cycle, right? So one stall is required here. Anywhere else, do we require a stall?
Ma'am, after add
After
instruction.
4.
Yeah, here also and after add also, I think. So similarly, one stall here also. What about store? If we see, this is the store instruction, this gets stored here, right? And let me see. So for the current instruction, add produces the result here. No, I don't think we require a stall here. We just need to forward. So this instruction, these two instructions can just do with forwarding paths. We just require two stalls into the entire code. One is after the first load, one is after the second load. Now the compiler sees that there is no independent instruction into the code, but it can always rearrange the instructions, maybe the ones which were getting executed later on can get executed earlier without changing the code sequence. So what it does is it just rearranges the code to remove any stalls. So yeah, and so this stall removed, right? So R1, after the load of R1, load of R4 takes place, and why this has come here? Yeah, and then do we require this stall now? Do we require this stall now? Earlier, this was taking place after the load of R4. Since load is happening earlier and then there are two instructions after it, there is no need for the stall also. So just rearranging the current code, it has removed any stall which was required in the pipelining of this code. This is called rescheduling, right? याद आ गया सबको?
Yes, ma'am.
Right. Now, to enhance this concept a little further, we will talk about removal of hazards into the pipeline using loop unrolling and scheduling. Now, see, we just saw that for this code, we had two loops. One was loading R1, the other was loading R4, and we just rearranged the code since there were enough ample number of instructions for rescheduling. But what about a code wherein we just have four instructions which are run 250 times or maybe 1000 times, right? So that in that case, we might not find any instruction which can be just inserted between other two instructions. To overcome that issue, the compiler of this DLX processor is quite efficient. Gurkirat, please mute yourself. Yeah. This is quite efficient. What it does is it unrolls the loop first. It opens the loop to find multiple instructions in the code and then reschedules it to avoid any stalls, while the code will run for the same amount of time as earlier. So let's take it up with an example. Whatever I said, I will illustrate that with an example now. So yeah, so let me just, yeah. So loop unrolling and scheduling. For codes that run in loops, we can exploit the instruction level parallelism to overcome the stalls in the pipeline. And yeah, so let us consider an example. Let us consider a program for adding a scalar value to a 1000 element array. All operations are completely parallel in this array. So we have an array of 1000 values, which is xi, right? And there is a constant s which has to be added to all the 1000 values in the array and in descending order. So it says I is equal to I minus 1 and it should go up to 1000. So it has to be in a descending order. And then finally, I don't know, something happened. Yeah, it's little displaced. Yeah. So this program will add a scalar to a 1000 element array xi and store the result at xi in descending order now. Now, let's write the code for this one. And here we go. So right now we have considered floating point numbers for the array. So load double into F0 from 0R1. This loads 64-bit value into register pair F0 and F1 from a memory location which is 0 plus R1. Base displacement addressing. So base register is R1, displacement is 0, right? Now, an add double F4, F0, F2 adds the value. See, we have the scalar, whatever constant we wanted to add, it is in F2, F3. So we have added F2, F3 to F0, F1 and the result gets stored to F4, F5. समझ आ रहा है?
Yes, ma'am.
All right. See, what is our main motive? We have to reschedule the code. Sometimes we do not have instructions wherein rescheduling is possible. So the compiler is so efficient with these processors that it unrolls the loop, maybe twice or thrice, according to the convenience. And then it inserts, instructions between two places where a stall was required, not disturbing the code execution sequence. And then the code will behave the same, it will run for the same time, it will take the same time to execute, just that stalls will be eliminated. So that is what we are seeing how it is happening in the LX pipeline, right? So we had this array of xi and this is a 1000 element array and we have a constant or a scalar which is in F2, F3 and we have to add it to the array values and store it back at the same location in the memory, and then this has to run for 1000 times, right? Okay, so load double into F0 F1 and add double F2 F3 plus F0 F1 and store in F4 F5, right? Now a store double, see we have added the value, it is in F0 F1 and the result is available in F4 F5. So we store double from F4 F5 to 0 R1 again. So again 8 locations in the memory fetched in one go. Since it was in descending order, we should decrement the counter by 8. So memory location decremented by 8 and then it checks if R1 is not 0, go back to loop. again load, again add, again subtract, again store, again subtract the counter, and then check. If it is not 0, go back, right? So this will run for 1000 times. Now if I just see the requirement of stalls here, now see, we are talking about floating point operations. A floating point operation and an integer operation might not require the same number of stalls. So there, the requirement of stalls for a floating point operation and an integer operation is different, right? So not going in much details, just to let you know how we are following the context of stalls here. If the previous instruction is a floating point ALU operation and the next instruction is another floating point ALU operation, we require 3 clock cycles. The latency or the stalls that we require are 3, right? If the previous operation is a floating point operation and the next operation is a store double, we require 2 stalls. If the previous operation is a load double and the next operation is a floating point ALU operation, we require 1 stall. This is fixed, bache. Are you all getting what I'm saying?
Yes, ma'am.
I hope this yes is for everyone. सबको समझ आ रहा है?
Yes, ma'am.
Okay, good. So the rule that we follow, so if the previous operation is a load double and the next one is a store double, we might not require even a single stall between them. Now moving next. So depending upon the current table, if we try and introduce stalls into the pipeline, so if the previous operation is a floating point ALU operation, so add double, and the next operation is a store double. How many stalls do we require here? See the table?
3 stalls.
2. It says 2.
2 stalls.
Yeah. So if the previous is a floating point ALU operation and the next one is a store double, we require 2 stalls. So previous is add double and the next one is store double, we require 2 stalls here. If the previous is load double and the next is floating point ALU operation, so previous is load double and next is floating point ALU, we require 1 stall. So 1 stall required here, 2 stalls required here, right? Anything
Yes,
else?
ma'am.
It's load double and yeah, I think we've covered all. So let's see how we have the unscheduled code, how it looks like. So the current code, if we see, after the load operation, we will have 1 stall here. After the add double, we will have 2 stalls here. And after subtract immediate and branch not equal to 0, let me see. Subtract immediate is an integer operation. So R1 hash 8, yeah, definitely. If we see, this produces the result in the execute stage and this checks in the execute stage only. So 1 stall required here. I hope this is clear.
Yes, ma'am.
For the previous operations, we consulted the table since these were floating point operations. A subtract immediate and a branch not equal to 0 are integer operations. We don't need any table for this. We just have to see where is the clash. If we observe, a subtract immediate produces the result in the execute stage and a branch not equal to 0 checks R1 in the same stage. So definitely it has to wait for R1 to update, right? Same clock cycle में clash हो रहा है ना? Should I write this for you?
Excuse me, ma'am.
हाँ जी बोलो बच्चे.
Ma'am, there were in the table there was also a stall introduced when there was the previous instruction was the floating point operation and the next instruction was a store double, but we haven't added any stall after that. Yes, ma'am. Like yeah, in the same instruction, add and
We
store
have
double.
no, we have introduced 2 stalls here. कौन सा बोल रहे हो?
Ma'am, after store double, won't be there any stall?
See, after store double, we have an integer operation, no? There's nothing which is mentioned regarding an integer operation over there. Otherwise, also, if we see, this stores the value of F4, F5 into location 0 up to 8 R1, right?
Yes, ma'am.
है ना? अब next instruction क्या है? Subtract immediate R1 hash 8. So this is a write after write operation. It is not going to make any difference unless there is some memory delay. Some memory delay cycles are introduced. Write after write hazard आ सकता है यहाँ, but वो worst case में आएगा. फिलहाल तो there is no discussion about it. I hope you're getting my point. See
मैम
this.
एक्चुअली
हाँ हाँ बोलो बोलो.
मैम मैं जो कहना चाह रही हूँ दैट इज कि जो टेबल थी उसमें दिया हुआ था कि अगर हमारा प्रीवियस इंस्ट्रक्शन एक फ्लोटिंग पॉइंट एएलयू इंस्ट्रक्शन है एंड द नेक्स्ट इंस्ट्रक्शन इज अ स्टोर डबल द सेकंड वन
Yeah.
टेबल.
So it
तो मैम
requires
देयर
two stalls. No, we have introduced
यस
two
मैम.
stalls here. See, we have introduced two stalls. Previous instruction is a floating point ALU
ओके
operation. Yeah. And the next one is a
ओके
store
या
double. Yeah. We have two stalls here. If you talk about store double, you know, updating a memory location 0 plus R1, and then we are updating R1 as R1 hash 8. This might lead to a write after write hazard if before the store this happens,
ओके ओके
right? So
Got
this is
that.
in a worst case. No, there is no mention about it. That is why I didn't take up. So right after
Okay,
write
ma'am.
hazard right now we are not considering, and it otherwise also happens very rarely. So if we just talk about this ALU operation, which is subtract immediate integer operation, and the next branch operation, right? If we just
Yes, ma'am.
observe, these two are dependent. This
Yeah.
updates the value of R1 and this checks the value of R1. And this happens in the same clock cycle. If I am not running
Yes,
short of time, what is the time right now?
ma'am. It's 2:42.
I have class till 2:40.
2:40.
Yes, ma'am.
Yeah. Yeah. Okay, I'll take this up again. But my point was to brush up everything today and start this up. So I think we are going in the right track. We can take this up again in the next lecture. And right now, I'm just ending the class. Okay, bache? Thank you.
Thank you, ma'am.